Okay, so for t greater than 0 and n greater than 0, we're going to let L of t equal the integral from 0 to infinity of e to the negative t x to the n over 1 plus x to the n dx. And we want to try and evaluate this in a more familiar form in terms of more standard functions. So what we're going to do is apply the Leibniz rule for differentiation. So L prime of t, that's just the derivative of our integral. And since the bounds are irrespective of t, we could just interchange these since this function here is bounded. In fact, it's bounded by the function 1 over 1 plus x to the n, which I have proved in another video. So then inside we get the partial derivative with respect to t, integrated with respect to x, and the denominator is independent of t, so we can just ignore that, and the top term will drop down a minus x to the n from the exponential by the chain rule. But as we can observe, this is quite close to the original function. We just need to add and subtract some terms. So if we add in well, we'll see in a second what I've added in. So I've had to add in a negative L of t. So I add it back in. And I get e to the negative dx to the n over 1 plus x to the n dx. Now moving down a little bit. So what do we now have? Well, this term here, that's just L of t. This term here, the term on the top and bottom of this cancels away. So now we're left with L prime of t equals the integral from 0 to infinity. It should be minus on that e to the negative dx to the n dx plus L of t. Now I've dealt with this in a previous video, this integral here. So rearranging, we get L prime of t minus L of t. That's equal to minus the gamma function n plus 1 divided by n times t to the negative 1 over n. Now, since my things just like to float away, let's just do that. So, what have we got now? We have got a first order linear equation, inhomogeneous differential equation, and we can use an integrating factor on this. So we'll just quickly find our integrating factor, pretty easy. The exponential of the integral of minus 1 dt from there. And well, that's just e to the negative t, ignoring any constants because they'll drop anyway. And if we now multiply through everything, we will end up with e to the negative t L prime of t minus e to the negative t L of t equals minus e to the negative t to the minus 1 over n gamma n plus 1 divided by n. Now the left hand side is precisely the derivative of e to the negative t times L of t. And the right hand side is just, well, this. Stays exactly as it was. And now if we integrate this with respect to t, and also we're going to apply bounds on this. So we want to integrate this thing from t to infinity. So then we end up with this, just simply applying the integral on both sides. And we can pull out the negative gamma factor to the front of the integral. So we're left with this term on the right. Now let's deal with the left-hand side first. Left-hand side is equal to the integral from t to infinity of a derivative. So by the fundamental theorem of calculus, this is just the integrand evaluated at the endpoints. Now we've got a note. From a previous video, I've shown that L of t is bounded by something of the form 1 over nth root of t, and this goes to 0 as t approaches infinity. So in fact, the top limit goes to 0. And plugging in t again, we just get e to the negative t L of t. Now to deal with the right-hand side, we're going to have to use the gamma function again. So I'll just get rid of this. So what is the right-hand side equal to? Well, minus gamma n plus 1 divided by n. And the integral from t to infinity, t to the... Now we want to make this in the gamma function form. We want this in the form for the gamma function. So we need a minus 1 here, but we can't obviously just add it in on its own. We need to add plus 1 in front. And then if you expand that fraction, you'll get n minus 1 over n minus 1 times e to the negative t dt. Now this is the upper gamma function, the incomplete upper gamma function, which you write as gamma of n minus 1 over n, comma t, which is the lower bound. And so we're left with this. Oh, my apologies, this should be a negative because we evaluated it at the lower bound. So minus gamma n plus 1 over n, incomplete upper gamma function, n minus 1 over n, comma t. Now these two sides are equal, so we could encapsulate away these minus signs, and we get e to the negative t, L of t equals gamma of n plus 1 over n times the incomplete upper gamma function n minus 1 over n, comma t. And just to get our final answer, we multiply both sides by e to the t, and we're left with this. E to the t times the gamma function of n plus 1 over n times the incomplete gamma function n minus 1 over n, comma t. And that completes this solution.